Bismillahirrahmanirrahim. Assalamualaikum everyone. I hope everybody is well during the MCO. So today we are going to do transistor sizing. Okay, so as you all know, there is an inverter. Inverter consists of a PMOS and an NMOS. Okay, so the inverter, we know the truth table of the inverter. When the input is 0, the output is 1, and when the input is 1, the output is 0. This means when the input is 0, the one that turns on is the PMOS, and when the input is 1, the one that turns on is NMOS. Okay, so now we want to look into the current equation for the NMOS. So as you all know, during saturation, ID equals to mu n COX over 2 W over L VGS minus VTN squared. This is the current at saturation. Now what we are going to do is we want to transform each transistor. We want to transform each transistor into a resistor. And we know that for the Kirchhoff law, V equals to IR. So if you want to know what is the equation for the resistor, it is the voltage over the current. So if we look at your transistor, this is an NMOS, this is the drain, gate and source, right? You have the voltage is across the drain, so R of the transistor, so R of NMOS is the voltage across the drain and the source, and the current here is IDS. Now if we want to calculate what is R of the NMOS is equals to VDS over IDS, and we know ID for the saturation is the one up here. So I'm going to substitute mu n COX over 2 W over L VGS minus VTN squared. Okay, so what is the condition at saturation? Okay, so let's look here. You know, for the NMOS, right? If you have the plot of the ID versus VDS, the current is going like this, right? And this region is known as the linear region, and this region is known as the saturation region. This point over here is known as VDS equals to VGS minus threshold. So at any voltage that is higher than VGS minus VTN, it is in the current is in saturation, and if VDS is less than VGS minus VTN, then it is in the linear region. So we want to replace the equation just now which was IR NMOS equals to VDS over mu n COX over 2 VGS minus VTN squared W over L, right? We want to put it at this point. So now we can replace VDS with VGS minus VTN. So VGS minus VTN over mu n COX VGS minus VTN squared W over L. So you can cancel this. Right? So now R and MOS, what does it become? It only becomes 1 over mu n COX over 2 VGS minus VTN W over L. Okay, so we have established that fact. So now we can replace the NMOS into a resistor R NMOS. Okay, the same way you have the inverter in and out. You can replace it into two resistors, and this is ground. This is ground, and this is R NMOS and R PMOS. Okay, and you have your in and you have your out. Depending on which one is on, it will be either connected to the PMOS or the NMOS. Okay, so now the R NMOS, which we calculated just now, is 1 over beta N. So you can replace VGS minus VTN. Okay, and R PMOS, because 1 over beta P VGS minus VTP. Okay, so in this case we are replacing, because this is connected to VDD, we replace this VGS with VDD. Okay, so beta N is not equals to beta P, therefore Rn MOS is not the same as the resistance of a PMOS. The resistor of the NMOS and the resistance of the PMOS is not the same. So it depends on your process parameter. So the beta N is equals to mu n COX W over L N, and the beta P is equals to mu P COX W over L P. Okay, so now the mobility of electrons is much higher than the mobility of holes. Okay, and usually the mobility of electrons is about 2 times mobility of holes. So in order to make beta N if we want beta n equals to beta p, so now your mu n COX W over L n equals to mu P COX W over L P. Right. You want to make it equal, but the mu n is not equals to mu P. So mu n is twice the value of mu P. So in order to make it equal, we have to multiply, because this is 2 times bigger than the mu P, we have to make the W over L, the W of the PMOS 2 times bigger. Okay, so let's see how do we do that. So now we can cancel the COX. We are left with mu n W over L n equals to mu P W over L P. Now you can substitute mu n equals to mu P. So 2 mu P W over L n equals to mu P W over L P. So now cancel. So therefore, the W over L of P is equals to 2 times the W over L n. Alright, so this means that for your inverter, okay, oops. If the size of the NMOS is 3 over 0.6, the size of the PMOS should be double, which is 6 over 0.6. Now, in terms of the R, this is RP and this is RN. Right? So the resistance, the initial resistance is Rn and Rp. So but Rn is not equals to Rp. Right? So if you look at V equals to IR and resistance equals to voltage over current, then since the current in the resistance in okay, how do I say this? The resistance in the NMOS is lower than the resistance in the PMOS. How do you know this, right? So we know that Rn equals to 1 over beta n VDD minus VTH, and Rp equals to 1 over beta P VDD minus VTP. Let's look at the second part, which is the resistors of the inverter. So now, if you have the inverter, okay, when the input is 1, right? So which one turns on? The NMOS turns on. So the NMOS now we can replace as a resistor. and it is connected to the ground. The output is connected to the ground. This is the R of the NMOS. The current is flowing down, right? So this is known as the pull down network. So the output is connected to ground and the current is flowing and the output is pulled down to ground. So the output will be 0 and this is known as the pull down network. Okay, so now when the input is 0, right, the PMOS resistor is activated and the output is pulled up to VDD. Therefore, the output becomes VDD or high, and this is known as the pull-up network. So we have the pull-down and the pull-up network. So the pull-up network pulls out the output to the VDD, and the pull-down network pulls down the output to ground. Okay, so here we want to know what is the value for NMOS and PMOS. So before this, we know that Rn equals to 1 over beta n VDD minus VDN, and if you do this, you expand mu n COX over 2 VDD minus VDN. Okay, Rp equals to 1 over beta P VDD minus VDP, and this is equals to 1 over mu P COX over 2 VDD minus VDP. So we know that because mu n is not equals to mu P, just now I had already explained, so therefore beta n is not equals to beta P. In order to make beta n equals to beta P, if we want beta n equals to beta P, therefore you have to multiply the width of the PMOS to be twice the you have to multiply the width of the PMOS to be twice the width of the NMOS. Okay, let me just correct this equation here. Okay, if you do that, once you have multiplied the PMOS size to be double the size of the NMOS, then you will only have the beta n equals to beta P. So now here, if you replace this is our PMOS and our NMOS. So initially Rp is not equals to Rn, but when Wp equals to 2Wn, therefore Rp is now equals to Rn. Okay, so now let's look at look at another example. Okay, we look at the NAND gate. NAND gate has two NMOS in series, A, B, okay, so this is the out, right? So it has two NMOS in series and two PMOS in parallel. So now you can see that the resistance here is Rn and Rn, and here is the resistance is Rp and Rp. Okay, the two Rns are in series, so Rn plus Rn, so the total resistance is 2 Rn. So now we look at Rp. There are two Rps here, they are in parallel. So if you know the resistance, the equivalent resistance equals to Rp times Rp over Rp plus Rp, which should be equals to Rp over 2, right? This is for the equivalent resistance. But for VLSI circuits, we need to look at what is the worst case. Worst case, this is the best case. Best case is that both resistors are on, both PMOS are on, and when the both PMOS are on, the resistance is Rp over 2. What about the worst case? So now, before I explain the worst case, let us look at the truth table of the NAND gate. 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. So in this case, which one is the pull up and which one is the pull down? So the pull up is the one that is connected to BDD. So this is the pull up, and this is the pull down. So the pull down network, there is only one case when both are on, so the resistance is this. So this is the pull down case. Case A equals to 1, B equals to 1. But what about the pull up case? The pull up case, these are all pull up case, and for R equivalent, when both PMOS are on, that is this one, this is the best case, right? A equals to 0 and B equals to 0, right? But what about when either one is on? Either one is on, so that means if A is 0 and B is 1, A is 0 and B is 1, that means this one is off and this one is on. So there will be a resistance here, Rp. So the resistance, equivalent resistance is Rp, which is single Rp, right? So now we know if we were to make, this is the same case for Rp if A equals to 0, B equals to 1, or A equals to 1, B equals to 0. So now when we put the full circuit, we have to put the worst case. That means this is the value of Rp, and for Rn, the value is 2Rn. So now comes the difficult part. What should be the size, right? The sizes of the transistors. So now let's say W over L for NMOS equals to 3 over 0.6. When you look at the inverter, right? When you look at the inverter, it was Rp and Rn, right? So let's look here. Oops. So if the inverter, in the case of the inverter, this Rp was replaced as Rp, and this was Rn, right? And because mu P is not equals to mu N, we had the sizes. We had the sizes 3 over 0.6, and this has to be double, so 6 over 0.6, right? So now in the case of this, for the NAND gate, you have this is Rp and this is 2Rn. If this is 3 over 0.6, what should be the width and L for the PMOS? So we know that mu N is equals 2 times mu P. So logically, usually, the W over LP should be double. But what about here? You see that the resistance of NMOS is double the resistance of PMOS. Why is it already double? Because there are two resistors in series. So this, in this case, because this is already double, so even you do not need to double this, so that they can have the same current. So the size should be the same. So let me repeat, what is the point of doubling the size of the width is so that the current here going in the pull down network and the current in the pull up network is the same. Right? And in order to do that, we need to look at the resistor. So the resistor of the PMOS is half the size the resistance of the NMOS. So because the resistance of the PMOS is half the size of the resistance of NMOS, when we were supposed to double, we do not need to double because this will compensate each other. Okay? So finally, the sizes of this would be 3 over 0.6, 3 over 0.6, 3 over 0.6, and 3 over 0.6. So all the sizes should be the same. Okay, so now let's look at the NOR gate. The NOR gate is the opposite, in which case the PMOS are in series and the NMOS is in parallel. Okay, so now if we look at the pull down network, the worst case here, this will be Rn, and for the PMOS series, the PMOS, they are in series, so they are Rp, so they would be, sorry, there's no connection to ground, 2Rp, right? In order for the same current to go up into the pull up network, is the same as the pull down network. So now what should be the size? So if the size of the NMOS is equals to 3 over 0.6, so now normally W over LP mu P is equals to mu N equals to 2 of mu P. So usually we have to double, but now you can see that the resistance of the PMOS is double the resistance of the NMOS. So therefore we have to multiply this. So normally you have to multiply by 2, but here because the resistance is double, because they are in series, you have to multiply by 4. Multiply by 2 because of this, because of mu P, mu N, and another multiply by 2 because of this 2Rp. So now the size of the PMOS should be 12 over 0.6. So each one will be 12 over 0.6. This is 3 over 0.6, 3 over 0.6. Okay, so I hope everybody understood, and if there is any questions, please let me know. Thank you. Assalamualaikum.